Hello, and welcome back to Learning with Lee. In today's episode, we are going to take a look at sorting algorithms, complexity, and big O notation. To begin with, we're going to go back over the merge sort algorithm, which we've already covered in the programming series that is on this channel. If you need to, you can go back through that series in order to find those episodes and rewatch them, because I'm going to go fairly quickly through going back over what the algorithm is, and I'm not going to explain it as in-depth as I did previously. So the merge sort algorithm happens to be, you have some array, and it has some number of elements, and for this I'm just going to refer to it as having n elements, and this is a very common thing. When we start dealing with complexity, you're going to very often hear me use n to represent the number of some thing that we are processing on. Because if you only have one thing that you're processing on, that tends to be a bit less interesting in terms of analyzing its complexity than in case you have a whole bunch of items that you're operating on, because that tends to be when you start to encounter problems in terms of your complexity getting too large or making it not feasible to really properly actually go through and compute the value that you're looking for in there. So I have some number of items, and the important thing to understand about this is that in the end I'm looking to get this in a sorted list, and the easiest thing to understand about a sorted list is that if I have only a single item, if I only have this one here in my list, and that's the only element, my list is already sorted. So the first thing you do in merge sort is you end up splitting it up into a whole bunch of arrays of of one size, so that they only have a single element in them. As a result, each and every one of these happens to be sorted already, because there's no other elements to sort them against. Then what you do is you end up pairing them up, and you end up sorting those pairs. So, in this case here, let's say that I had elements 2 and 1 in there. I would go, okay, is 2 less than 1? No, it's not. Put 1 in the first element here, put 2 down here. And then I would end up repeating that basically at the next higher level up, and compare that with this one here. And there's a few important things to understand about this. The first is that we end up effectively having the problem at each one of these steps. And by a step, I'm referring to basically one of these different layers in here where we have a new larger number, basically larger size of our base array. So in this case here it would be 2, in this case level would be 4. In case we had an arbitrary number, not these 6 that I'm showing here, we would have a whole bunch of these that were 4, then we'd have a whole bunch at 8, then 16, and so on and so forth. And what you can see with that is that the size of our array at each layer, and this is a bit not necessarily as intuitive for those who are less familiar with exponents and with logarithms, but basically at this layer here, we happen to have 2 to the 0 for the size of each one of these arrays. So we have one element. And for those who aren't familiar with exponents, whenever you raise something to the 0, happens to be 1. And some of this is going with the typical computer science notation of saying that we start at 0 and then we have step 1. And at there, our arrays are 2 to the 1. At this level, they're 2 to the 2, or less. The important thing to remember is that this happens to be the maximum size of our arrays at that level. At this level here, it's 2 to the 3. And it'll keep going that way, so on and so forth. So what you have, then, is you have 2 to the L for basically the number of levels. And what's important is that eventually what you're going to care about is that this 2 to the L is going to need to be it's going to need to be greater than or equal to n, so that we can store all of our array sorted, which is n numbers, within that amount, within that level. And the way in which you would then represent that is that the number of levels that you have happens to be, so L would be greater than or equal to, and what we would look at then is the log base 2 of n. And that just is another way of rewriting this and another way of sort of solving for it. And I'm not going to get into logarithms in this series or in this episode. In case you aren't as familiar with logarithms and would like me to have an episode or two going over logarithms, feel free to post in the comments about that, and I will, if I have the time and the ability to do so, I will endeavor in order to create some episodes about that, but only in case that's something that you guys happen to be wanting me to do. So that's one of the important things, is that we have effectively log base 2 n layers. That's the number of layers that we're going to have, because realistically what we can say is that because we don't care about the greater than side of it, really all that we want is we only care about it if it's equal to it, for this case here. Technically there might end up being more space available to us at that level than log base 2n, but that ends up being the number of levels that we're going to end up doing. And then at each one of those levels, we're going to do a total of n steps within there. And the reason that we're doing n steps is that at one of these levels, such as this first level here, I need to compare these two. So there happens to be one operation for that comparison. Then I need to copy this one over into here and copy this one down into here. And as a result, basically, even if I end up copying this 2 directly across here and this one directly across here, I'm going to wind up having to do a total of n steps because of the fact that I'm going to have, well, technically it's a bit more than n. However, as we're going to get into in a little bit, with a lot of this stuff related to big O notation and complexity, you tend to round to the nearest polynomial number or the largest polynomial that you're dealing with. So in this case here, because of the fact that we're dealing with n steps, because we have to go, okay, here's 2, I must copy this one over, and I must copy this one over, that's going to be, in each of those cases, 1 step, and I'm going to have to do that for every single element in my array. The total number of comparisons is going to vary based upon level and based upon the specifics of each level. Because if at this level here, I then happen to have something like 0 and 4, what's going to happen is that 1's going to get compared to 0, 0's going to get moved in, 1's going to get compared to 4, 1's going to get moved in, 2's going to get compared to 4, and then it's going to get moved in. So basically what we wind up with is, in each of these clusters, we have the number of that cluster minus 1 comparisons, but then we also have that number that we then have to move over. And as a result, the more significant of those two ends up being n, because it's going to end up causing us more problems in the long run. But that's something that we'll get into once we start getting into things like average complexity, because average complexity cares about some of that specifics. So that is merge sort, and the important thing to understand about that is because we're doing n steps at each layer, you can sort of think about it like this. We have, and if you prefer, you can think about this in terms of like Minecraft blocks, you can think about this in terms of chunks of memory. It doesn't really matter. But what's going to happen is that we're going to have some little value in here, and I'll just switch back to brush now. And what's going to happen is that we're going to have some number of steps, and these are going to be our log base 2 number of steps. Whoops, log base 2n steps. And then within each one of those, we are going to have n operations that take place. Or technically it's slightly more than n, but as I said, n operations that take place. For that then, we want to know the total number of operations that are going to take place for this algorithm. And as you can guess from just basic geometry of finding the area of a rectangle, what you do then is you multiply these two together. So what you wind up with is that the complexity of merge sort is n times the log base 2 of n. So that happens to be how you determine the complexity of your algorithm in terms of its computation. And the complexity is just the number of steps required to do that algorithm, to do that operation. And the important thing about saying this with this n log n, well, n log base 2n, is technically that's your worst case complexity. And your worst case complexity is your big O complexity. So what you do is you go big O with then parentheses after it, and then whatever the complexity is within there. So in this case here, it's big O, or if you want to, it's also referred to as order. So you say that you have order n log n complexity. And very often log base 2 is just shortened to log in computer science, because almost always whenever you're dealing with anything that's a logarithm in computer science, it tends to be base 2. And occasionally you'll run into algorithms that aren't, but it frequently, if not always, happens to be that base. So now for some slightly less efficient algorithms. And those happen to be selection sort, insertion sort, and bubble sort. And they're 3 different varieties, but they all have some very similar operating parameters for how they work. With selection sort, what you do is you go through your list, and I'll use this one down here as the example, and you find the smallest number, provided that we're looking to do it from least to greatest, which is sort of why I have this arrayed from greatest to least, so that we can see sort of how it handles in not necessarily the worst case scenario, because there are actually worst case scenarios for selection and insertion sort. But what it does is it goes, okay, find me this element here and move it over here and basically end up swapping those. And all of these are going to rely on swaps. So then what you have is you have 1 here, the same array here, and 6 here. And that's your first step. Then your second step is you have to search through this for the next lowest value. In this case, it would be 2. And you would swap it with whatever's in the second spot. And then you would wind up with 2 here, 5 here. And technically, these ones here, even though they've been moved there, they're still unknowns. Realistically, if I want to, I could say delete this. And because this is the only section that you actually know is sorted. Because this could just as easily over here be a 9, so it could end up being with 6 back here and 9 here, so we would still have to sort those. And that's what this little diagram up here is showing you, is that with every single one of these, what you're doing is you're finding basically a subset that is sorted, and then you're removing one element from the unsorted list and adding it to the sorted list. And each one of these varies depending on how they end up doing it. However, every single one of these, because of the fact that in case you want to go with something like searching it, because searching through an unsorted list, if it's completely unsorted and you don't know anything about it, you have to inspect every single element in there. That means that every single one of these, we're going to have to do n total steps in order to search through it for the one that we're looking for. It's a little bit different for insertion and bubble sort, but they still end up having n steps. They just go about it in a different manner. What then ends up happening is that we have n of these tiers. Technically, this final tier, we could say that we have n minus 1 layers, because once you're down to a pair of elements, and the rest of your list is sorted, you only have to really sort those 2 elements. So you can do some shortcuts so as you don't have to do as much work on it. And technically, the amount of searching that you need to do goes down. And you can sort of see how it forms this little triangle in here for it. So technically what ends up happening is that you have effectively n times n over 2. So you wind up with a triangle, and as I was mentioning with area before, you have effectively these n steps that you have to do here, and you're going to wind up with n over 2 for the total number of searches you have to do within each one of those. Because initially I have to do 6 searches in order to find this 1, then I have to do 5 searches to find 2, 4 searches to find the next value, which in this case here is 3, and so on and so forth. Because even once I'm down to this little thing where it has 1, 2, 3, 4, 5, 6, I don't necessarily know that 4 is the smallest number in there. I could do some stuff involving caching to possibly help me out, but the thing is that that's still such a niche case that that isn't really the necessarily best way in order to do that. Though I could see for certain applications wanting to do some caching of basically these ones you've already seen in order to be able to deal with the cases where you have some sorting already taken care of for you. But typically it's going to just add in additional problems and additional complexity beyond what you were already doing. So then it has to go, okay, well, is 4 the smallest amount in my remaining subset? Yes, it is. Okay, let's then add it in to this subset over here and say that that's sorted. Then I have to check for these 2, which one's the smallest one of those 2, and swap it into its correct position. And that will wind up being how you end up doing selection sort. For bubble sort, what that is it's a little bit different. And for this I'm going to need to actually just undo a whole bunch of this real quick. What you end up doing there is you go, I am going to basically say, this is now sorted because there's one element here. Then I'm going to add in an unknown element into that sorted list. And it's going to be like, okay, is this number less than this number? Okay, swap those two numbers. Then I'm going to add in this number. So right now our list happens to be 5, then 6. So then I add in 4. And what's going to happen is that it's going to go, okay, is it less than this number? All right, swap the two of them. Then, is it less than this number? Swap them again. And it's going to repeat that all the way through here. So basically what we wind up with then is we wind up with 5, 6 being sorted. We wind up with 4, 5, 6. We wind up with then 3, 4, 5, 6. And you can see how this is going, and you can see how it ends up forming this sort of triangle here, where on one side happens to be the number of steps that we have, and on the other side happens to be the number of bubbles that we have to do. And once again, this is the worst case complexity. It's going to vary because for something like selection sort, insertion sort, and bubble sort, their best case complexity, in case the thing is entirely sorted already, is that they have to do zero work. Because they don't have to do any bubbles, they just do a few comparisons. And technically you could argue that that's order n in order to do those comparisons. So, realistically, for how it's actually implemented, the best case scenario is order n, because it's going to have to go through and just check that it actually happens to be sorted. In theory, in terms of how you just view it at this high level, it tends to be described as having a order of 1. But the fact of the matter is that typically what you're going to wind up with is an order n for your complexity in actual real-life implementations of it. But it's a matter of you wind up getting these triangles effectively is how you can view it, and that's why you wind up with this n squared, because what you wind up with then is you have n times n, and because it's a triangle, it's 1/2 n times n. So insertion sort, once again, very similar to the other ones, starts off with selecting this first item here. And sorry for just using the term selecting, but it splits off the first item so it's in a sorted list. What then does is it splits off the second item and adds it to that sorted list. However, unlike the other ones that ended up bubbling, as well as also ended up going, okay, I need to then swap for selection sort, what this one does is it takes this one and it goes, okay, I'm going to move it into this one here and move everything after it 1 to the right. And this ends up being the whole problem here, is that you take your first one here, and it actually ends up being a bit more ugly and to a certain extent complicated than even selection sort or bubble sort is. Because what you have to do is you have to go, okay, I have this one here, I need to figure out where in this sublist it belongs. So what I'm going to do is I'm going to have to check it against every single one in there until I find one that happens to be less than. In this case here, it does a single check, and it goes, okay, I'm going to put it here, and I need to shift every single one that's after it to the right. And then you wind up with 5 and then 6. But it's important to remember that shifting to the right is also an operation, just as the comparisons themselves are operations. So its best case is also slightly worse than some of these other ones. So then for 4, what you would then do is you would go, okay, I'm going to take 4, I'm going to stick it at the beginning of the list here, but that means that 6 needs to move over here, 5 needs to get put over where 6 currently is, and you have to do some stuff involving memory to do that. And you can do some stuff using memmove in order to make this slightly more efficient in C, but for any higher level language like C++ or Java, you pretty much have to hope that they have it implemented for you, and to be fair, almost all of them do, and almost all of them have things like merge sort and quicksort implemented for you. And I haven't gone over quicksort, but quicksort is just a variation on merge sort, except you basically, rather than splitting it in half and then splitting in half again until you reach these down here, what you wind up doing is you basically go, if I want to split it at a third of the way through, because let's say that I happen to have some knowledge about how my list is already sorted. And this is where it can really excel for you, is that in case, say, you already knew that this section of your list was already sorted, then you would only have to focus on this section here. Same thing for if this section up here is already sorted, then you can end up saving yourself a bit of time. But it's similar to merge sort, it just has this arbitrary cutoff that you yourself decide upon. And there's some other situations where that ends up being a bit more efficient, but we're not going to get into quicksort in today's episode because it's already been a bit long. So for now, I'm going to really focus on what are the key points I want you to understand about this. The key things that I want you to understand are merge sort, though I can understand why you might want to go back through the other episode I've already had on that in order to understand that better. In the next episode, I'm actually going to provide you with an implementation of selection sort, insertion sort, and bubble sort, just so that you can really see how they're actually done in code, and hopefully spend a bit of time studying that in order to understand why I described it as this triangle here of you end up getting slightly less things to process at each iteration. However, at the same time, you start out with basically n items that you need to process in one iteration, and it goes down to effectively one item that you need to process, though I've cut that step out of here for the fact that realistically in code you actually would shortcut that most likely. Your code's a bit cleaner if you don't shortcut it, but you do also add in a bit of extra work that you have to do then. Though to be fair, that shortcutting adds in extra work to each of these layers, so that's one of those problems of a trade-off that you have to deal with. And that has n steps to it. And the important thing to understand about that is that that ends up resulting in your worst case complexity. And that's what your big O notation is. Your big O notation is your worst case complexity. The most number of steps you will need to do to solve this problem. And typically what you care most about are your worst case complexities and your average case complexities. And I'll get into average cases complexities in the future. The issue is that they are significantly harder to compute. Because what you have to figure out is, for something such as bubble sort, how many of some arbitrary length array end up being solved for by a single bubble? How many get solved for by 2 bubbles? How many get solved for by n bubbles? And so on and so forth. And that ends up being significantly more complicated, and typically, for most algorithms, you can figure it out without having to just brute force write out every single iteration. You can logically think about it. However, it is a more complicated computation, and typically your big O notation, your worst case complexity, is good enough. And frankly, your best case complexity, which is also something you can compute, tends to be fairly worthless, because very rarely are you already going to be in a best case situation when it comes to things like arbitrary data. And there are other things you need to actually consider with these that we haven't even gone into yet, and that's things such as memory considerations. And that's that for these situations here with selection, insertion, and bubble sort, you can do these operations on a single array without requiring anything more than effectively one element size data to do the swap. Because what you do is you move basically 1 out over to here, you then move 6 over into here, and you move 1 back over into here, in case you end up doing something like selection sort. So you don't actually need that much of additional space for it. And in the real world, memory actually becomes a significant problem. In theory, it doesn't necessarily end up being an issue, and it's something that very often will get glossed over in educational courses, in things such as business interviews and the like, but the fact of the matter is that in the real world, you end up having to deal with things such as paging, you have to deal with caching, you end up having to deal with real-world issues that will result from you having too much stuff in memory. So memory does become an issue. So the fact that for this case here, you end up, well, at least in the examples that I've already shown previously, you end up using 2 arrays to do this, and theoretically, if you really want to, you could do it with only a single array. It just would increase the amount of computation that you have to do at each one of these layers, at each one of these steps. So it ends up having 2n for its memory complexity. But memory complexity is something that we'll get into in the future as we start comparing and contrasting different solutions. And we'll take a little bit of a look at in the next episode as we start comparing the implementations of all of these different sorting algorithms. So, thank you very much for watching. Have a wonderful day.